All right, so here we are in lecture 20 of our course on real analysis. And what we're going to discuss today is how the notion of continuity of a function interacts with various topological properties of sets. So to motivate this, recall the very important theorem from calculus known as the extreme value theorem. The extreme value theorem says that if we have a continuous function on a finite closed interval from a to b, then this function has maximum and minimum values. Okay, so the function can't go to infinity or negative infinity. And furthermore, those values are attained. So there's actually, there are numbers in this interval for which the value of the function on those numbers is equal to the maximum and minimum values. Okay, so this is a famous and important result from calculus. And if we think a little bit about this theorem, about this, especially about the domain here, this finite closed interval, AB. If we try to weaken this, if we try to mess around with this interval at all, we find that the theorem no longer holds. So for example, if you take this interval and you replace it with one of the half-open, one of its half-open analogs or the fully open interval, it's easy to construct examples of continuous functions that do not attain a maximum or minimum on those intervals. So the theorem no longer holds if your interval is not closed. And furthermore, we can maintain the closure of the interval, so we can replace the interval, this finite closed interval, with an infinite closed interval. So you can consider the infinite closed interval from a to infinity or from negative infinity to b. But it's easy to see that in these cases, the theorem doesn't hold either. So you can again find examples of continuous functions on such intervals which do not attain a maximum or minimum. Notice these intervals are closed, but what they aren't is bounded. So that's how they differ from this finite interval from a to b. So we found that the notion that the interval be closed and bounded is a very important component of this theorem. So then it's rather natural to wonder whether these are the key properties that this interval has, or whether it's essential also that we have an interval here. So it's quite natural to wonder whether the sort of things that are driving the truth of this theorem are just the closed and bounded property of the interval, or whether the fact that it's an interval is actually essential. And it turns out that it's not. So we have this general extreme value theorem, which tells us that as long as we have a continuous function on a compact set, so this compact set could be a subset of Rm. Okay, so we have a real valued function on a compact subset in Rm, and it's a continuous function, then this function is bounded and takes on its maximum and minimum. Okay, so there is a maximum minimum, and the function attains that maximum minimum. So the way you can say that is that there are points in the domain k, x1 and x2, such that f of x1 is bigger than or equal to the value of the function at every other point in k. So this is your maximum, clearly your maximum. And then you have an x2 where the value of the function is less than or equal to the value at all other points in k. So that's your minimum. Okay, so this says we have a maximum minimum and they're attained at these points, x1 and x2. And so probably in calculus, you didn't see any proof or even indication of a proof of this theorem. It just was presented as sort of intuitively clear. But we want to actually go over a proof in, one of the sort of main objectives of this course is to do a proof of that theorem, and that's what we're going to do today. And the cool thing about the proof of this theorem is that we're not going to prove the theorem by sort of looking at what we're given in the theorem and then trying to go to make some straightforward argument that we can produce these x1 and x2 with the required properties. The proof here is actually going to be a consequence of another theorem, which comes about by asking some rather natural questions about continuous functions, given the topological properties we've been discussing. So, for example, some natural questions would be, if we have a continuous function, so what we're going to do is look at various types of sets and ask whether this continuous function preserves that type of set. So for example, if U is an open set and f is a continuous function, is f of u open? And if f is a closed set, capital F is a closed set, is little f of big F closed? If k is compact, is f of k compact? And finally, if S is connected, is f of S connected? So these are some fairly natural questions to wonder about once you have the concepts of continuity and these various topological things, open, closed, compact, connected. Once you have them all available to you, these are fairly natural questions to present themselves. And we'll see, in fact, that the answer to 3 basically implies the extreme value theorem with very little effort. So if we can answer 3, then we'll be able to prove the extreme value theorem. So let me just get a color here. So this here, this is going to lead us directly to the extreme value theorem. And so I guess I should say the answer here is yes. So the answer is yes, and that leads to the extreme value theorem. The answer to 4 also turns out to be yes. So this is fairly intuitive. So if you sort of intuitively think about what connected means and intuitively what a continuous function is doing, then a continuous image of a connected set should be connected. So you kind of expect the answer to this to be yes. And this is going to immediately imply, well, more or less immediately, imply another very famous theorem from calculus, which is the intermediate value theorem. Okay, so we have 2 value theorems, extreme value theorem, intermediate value theorem, both implied by these very rather natural questions about how continuity interacts with certain topological notions. As for 1 and 2, these are easily seen to be no. Okay, so just some exercises for you. So these are easy exercises. You should be able, with not too much effort, be able to produce some continuous function and open set such that f of u is not open, and some closed set and continuous function so that the image of that closed set is not closed. All right, so here's the formal statement of the answer to the third question above. So this is the theorem that says that continuity preserves compactness. Okay, so we're just going to have a compact set, a continuous function. The image of that compact set is compact. So here K is our compact set. This is quite general, so we have a compact set in Rm, continuous function from that compact set in Rm to Rn, and then we have that the image of that set must be compact. So here is the proof. Okay, so the main thing we're going to use is the sequential characterization of compactness. So first, we're going to recall that a set K is compact if and only if every sequence in K has a subsequence which converges to something in K. Which converges to an element of K. So for us, this was a theorem So in these lectures that I'm giving, the definition of a compact set was a closed and bounded set, and we showed that this was an equivalent characterization. In the text, in fact, this is the definition of a compact set, and then closed and bounded is an equivalent definition. That's a theorem, that it's an equivalent definition. Okay, so for us in these lectures, this is our a theorem, a consequence of the definition of compactness, whereas for the text, this is the definition of compactness. Okay, so this is one of the main two ways you can think about compactness. And the reason that we use this definition of compactness is because continuity, remember, continuity tells us that if we have a sequence xk converging to x, then f of xk has to converge to f of x. So, we have a kind of sequential characterization of continuity. We have a sequential characterization of compactness, and so those two things are going to play nice together. So that's kind of the underlying idea that motivates using this definition, this characterization of compactness. Okay, so let's just put this in parentheses here, and we'll start the proof proper down here. So to show that f of k is compact, let, say, yi be a sequence in f of k. And what we have to do is show that there's a subsequence that converges to something in f of k. Okay, so by definition, this yi is in f of k, so that means each yi is f of something. Okay, so we have yi as a sequence in f of k. So since yi is in f of k, we have yi equals f of something, f of xi, for some xi in k. So this means, so therefore, we have a sequence. We have a sequence xi in k. And, well, k is compact, right? We have a sequence in k, and k is compact. So we're trying to use this fact up here to prove that f of k is compact, but in the middle of this, we also have to use this fact when we're talking about the set k itself. And so we're kind of using this fact two different ways. We're using it on f of k, and we're also using it on k. So we have the sequence in k, and k is compact. So there is a subsequence there's a subsequence x sub I sub j, okay, sequence indexed by j, and it's converging to some x in k. And, well, I think you know what we're going to do, right? I mean, we're just going to, we have this sequence converging, and we have this f which is continuous. So the function is going to preserve this this limit, right? So the f of everything, the f along this sequence is going to go to f of x. So since f is continuous, we have f of x sub I sub j. That sequence, as indexed by j, must be converging to f of x. But then just remember that the y's are exactly the f of the x's, right? But this says this just says that y sub I sub j converges to f of x. And f of x, by definition, is an element of f of k. So our sequence yi indeed has a subsequence which converges to something in f of k. And so f of k is compact. And that's it. Okay, relatively straightforward argument. Once you decide to use the sequential definition of compactness and the fact that that a function sort of preserves convergence or kind of commutes with convergence, it's more or less, so the proof. I mean, you write down the properties and it sort of just leads you by the nose, right? You start with a sequence here, it gives you a sequence in X. You immediately get a convergent subsequence, you apply the function, and it's just almost straight line through the proof. Okay, very natural. So this, so the naturalness of the proof reflects the naturalness of the question. Okay, so nice and tidy result there. All right, so as a nearly immediate consequence, we can prove the extreme value theorem. So just remember, extreme value theorem here, we have a continuous function on a compact set into the real numbers. We need the real numbers here, so we have so we have an order, so we have some notion of sort of largest value of your function. And so what we're supposed to do is produce a maximum and minimum for this function. Okay, so let's see how this works given the preservation of compactness under continuous functions. It's sort of evident how you should start the proof, right? We have a compact set, we have a continuous function, so f of k must be compact. All right, so since f is continuous and k compact, f of k is compact by the previous theorem. Okay, so, well, since f of k is compact, what that means in particular is that f of k is bounded, right? So there have to be, so definitely a maximum, f of k sort of can't extend to infinity and negative infinity, right? So that seems like a relevant thing to notice for trying to produce a maximum and minimum. We need to know that the function actually doesn't extend infinitely far to the right and the left. So since f of k is bounded, is compact, it is bounded. And well, so we have a bounded set, right? So it's bounded from above and bounded from below. So by completeness, it has an infimum and a supremum. So by the axiom of completeness, f of k has a sup and an inf. So let's just say S is equal to the sup of f of k. And I don't know, I don't like to use inf, but that's the same thing as greatest lower bound. So we'll just say G is equal to the inf of f of k. So if you're picturing this, let's see. So I mean, this f of k, might look like kind of potentially random looking set of points, but we are going to have, right, you have the sup S and the inf G. Right, so these are kind of clearly your maximum and minimum. All you have to say now is that S is actually in this f of k. So in other words, S is f of something, and that G is in f of k. So G is f of something. And so to do that, so we just have to say that these numbers, S and G, are in this set f of k. And so far, the fact that f of k is compact, right, that's sort of our main conclusion of the fact that f is continuous and k is compact, is that f of k is compact. So far we've used bounded, right? We haven't used closed yet. And that's going to allow us to conclude that S and G are in f of k if we invoke the fact that f of k is closed. So it's a general fact. So in general, if the sup or inf of a set exists, then it is in the closure of the set. Then it is in the closure of the set. This is a pretty straightforward, easy exercise. So I'm not going to interrupt the flow of the proof to demonstrate that. So thus, S and G are in f of k closure, but that is equal to f of k, since f of k is already closed. Since f of k is closed. All right, so this follows from our characterization of compactness as being closed and bounded. But this means that S equals f of x1 and G equals f of x2 for some x1 and x2 in K, and that completes the proof. And clearly, f of x1 is bigger than or equal to f of x. F of x2 is less than or equal to f of x, right? Because f of x1 is S, that's the sup, that's the, it's a greater, it's an upper bound for the set f of k, right? So it's bigger than or equal to everything in f of k, everything in f of k has the form f of x, and then similar argument for f of x2, using that f of x2 is a lower bound. Okay, so f of x2 less than or equal to f of x for all x in k. And that completes the proof. Okay, so there's one of the most significant and famous theorems from calculus and its demonstration. So it's probably worth noting how straightforward, how not that difficult the proof of this theorem is for us at this point in the course. And that's because a lot of the complexity of it is kind of hidden in our definitions and the concepts that we've developed. So for example, we've fully and carefully defined the notion of a function being continuous. We defined the notion of a set being compact, and we have multiple ways of thinking about this. One in terms of sequences, right? So we have a sequential definition of compactness, and the fact that that definition is equivalent to the set being closed and bounded relies on the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem relies on the axiom of completeness, right? And we see in this proof we're also invoking the completeness axiom of the real numbers. And so, there's a lot going on in this proof, as short and kind of straightforward as it looks right here. So we had to really dig into the nature of the real numbers themselves, right? Knowing the completeness axiom and having some rather precise notion of what the real numbers are and how to talk about them, and then sort of noticing the relevant concepts about sequences and subsequences, and what the notion of continuity is. There's a lot of complexity being layered on complexity here in this proof. So you should take a second to appreciate how easy this might seem compared to how difficult it really is when you start pulling apart and looking at all the pieces individually. So it really is kind of a marvel of ingenuity and just hard work over many centuries of mathematical thought. All right, so now we'll move on to that fourth question we asked, which is about how continuity and connectedness interact. And we said that the answer to that question is yes, and I think that's a relatively intuitive result, that if we have a continuous function and a connected set, this is a connected set in Rm, continuous function from that set to Rn, then the image of the set is indeed connected. So let's look at the proof. All right, so I'm going to recall a fact again. So recall that S is connected if and only if whenever we write S equals A union B, so whenever you split S into two pieces, S equals A union B, where A and B are non-empty and disjoint, okay, so this is the D and the N in Don, right? So we have a disjoint and non-empty, looking like a separation of S, but S is connected, so it can't be a separation. So that means that these A and B can't both come from open sets. And a consequence of this, so this is a theorem that we proved, and it's the main theorem in the section on connected sets in the text, if you're looking for a reference. So what it says is that if you try to, right, so if you try to separate S like this, you can do disjoint and non-empty, but you can't do the open part. And one way to say that is that the closure of one of these sets has to bleed into the other set. Then the closure of A intersect B, or A intersect the closure of B, are non-empty. Okay, or maybe I should say then at least one of those two sets are non-empty. Okay, so this is kind of the positive characterization of connectedness. Remember, the definition of connected is actually that it's not disconnected. So you give a definition of disconnected, and then connectedness is just the negation of that. So this is a way of characterizing connected without using a negation. Okay, so that's our characterization of connectedness, and we have to show that f of s satisfies this condition. So what we'll do is write f of s equals A union B, where A and B are disjoint and non-empty. Okay, well, what we have to work with are that f is continuous and that s is connected. Okay, so we're over here in the image of this function, right, f of s over here in Rn. We have that s is connected, so somehow we want to take this, this sort of, well, not actual separation, this writing of f of s in this disjoint form. We kind of want to pull that back to a sort of similar decomposition of S. Okay, so naturally what we're going to do is we're going to look at everything in S that maps into A and everything in S that maps into B. Okay, so what we're going to do is consider F inverse of A and F inverse of B. Okay, so F inverse of a set. So I just sort of give it a general definition. F inverse of some set X, this would be, or maybe I'll say Y. So F inverse of some set Y, this would be all of the X such that F of X is an element of Y. Okay, this is called the pre-image or inverse image or pullback of Y by F. And just everything that F is dumping into that set there. All right, so this set F inverse of A, this is just everything that's going into A by F. And so if we kind of look at, I don't know, if like our picture of S is this, and we have A and B, so this is S over here, we're looking at, or sorry, this is F of S in our picture. So this is F of S, we're just looking at everything that's sort of, so over here is S, we're looking at everything that is going into A. All right, so that would sort of be, that would be F inverse of A, and then we have F inverse of B, that would be everything that's going into B. Okay, so hopefully I'm making sense here. So clearly S equals F inverse of A union F inverse of B, and F inverse of A, F inverse of B are disjoint and non-empty. Okay, so let's see. So why are these disjoint? Well, if you have something in F inverse of A and something in F inverse of B, then that means its image has to be in A, but also in B. But the problem with that is that A and B are disjoint. Okay, so the fact that A and B are disjoint implies that F inverse of A and F inverse of B are disjoint. So why are they non-empty? So why is F inverse of A non-empty? Well, A itself is non-empty, right? So there's something in A, but by definition, A is in this F of S, right? So A is F of something. Okay, so that something is ending up, is getting mapped into A, so that something is in F inverse of A. And the same argument applies to F inverse of B as well, to say that that is non-empty. And why is S equal to this union? Well, that's actually rather straightforward, right? So you just take something in S. If you have something in S, then F of that something either lies in A or B, right? So if that, F of that something lies in A, that exactly says that that something is in F inverse of A. And if it lies in B, that exactly says it's in F inverse of B. So it's in one, it's in either this or this. right? So that says S is contained in here. And the other inclusion is trivial because this F inverse of A, for example, well, to be an F inverse of A, right, you have to be mapping into the set A, so that means you're in the domain of the function, right? And our function is only defined on this S, so that has to be in S. Okay, same thing with F inverse of B. Okay, so now we have this disjoint non-empty decomposition of S, but S is connected. So since S is connected, then it has to be the case that the closure of this set is intersects with this set, where the closure of this set intersects with that set. Since S is connected, F inverse of A closure intersect F inverse of B, or F inverse of A intersect F inverse of B closure is non-empty. So without loss of generality, right, just by relabeling A to be B and B to be A, it doesn't matter. So without loss of generality, say that F inverse of A closure intersects F inverse of B is not the empty set. And let's say, so take X in this set. Okay, well then X is in F inverse of B. So we're basically just writing down what are the properties of this X being in this set. So X is in F inverse of B, so F of X is in B by definition. And X, well, if X is in F inverse of B, it can't be in F inverse of A, right? So it must be a limit point of F inverse of A, because F inverse of A and F inverse of B are disjoint, as we said. Right, so it being in this one means it's not in here. But it is in the closure, so that means it must be a limit point. And X is a limit point of F inverse of A. So thus, there is a sequence. So there's a sequence of xi contained in F inverse of A such that that sequence converges to X. But then this is where the continuity of F, so now we have to, and so we've sort of done a bunch of work over in the domain side, but ultimately we're trying to show that F of S is connected. So we sort of have to make a transition back to the other side. And this is where the continuity comes in, because we have this converging sequence. So the F, applying F to that convergent sequence will also give us a convergent sequence. But by the continuity of F, but F is continuous. So F of xi converges to F of x. And F of x is in B. But F is continuous, so we have that. And xi being in the inverse image of A implies, or exactly means that F of those things are in A. So what we have, we have a sequence in A converging to an element of B. So this implies that this element of B is a limit point of A. And so remember, A and B are disjoint, so f of x can't equal f of xi for any of these xi's. So that tells us that f of x is in fact a limit point of A. Okay, and so we have a sequence in A converging to an element of B, and since A intersect B is empty, this element is a limit point of A. Thus, the closure of A intersect B is not the empty set. But remember, that's exactly what we were trying to show to say that our set f of s is connected. Right? We took this disjoint and non-empty. We have to go up to our definition here to say it's connected. We want to say that the closure of one of them intersected with the other one is non-empty, and that's exactly what we just did. So f of s is connected as claimed. So just as with the extreme value theorem, how that followed from the preservation of compactness under continuity, we get as a consequence of the preservation of connectedness under continuity, the intermediate value theorem. So you'll recognize the statement from calculus. I'm sure this theorem doesn't need too much introduction, but just recall that what this says is that if we have a continuous function, so this should say, so suppose f is continuous. So we have a continuous function, and let's say that f of a is less than f of b, and we have some value y in between there. Then that value y is hit by the function f. Okay, so there's some x in between a and b, such that f of x equals y. And the basic idea of this is quite simple. It's just from the previous theorem. Right? So the visual is simple. If you have AB here, right, then you can kind of picture the graph. Right? So you have f of a. So let's say you have f of a here, and you have f of b. So the graph can look, typical continuous function graph. Graph looks like this. Well, by the previous theorem, the image is connected, right? So that means that basically what's going to happen is that the image of this interval AB is itself going to have to be an interval, right? So it's going to be this interval here from whatever this value is to whatever this value is. And so since that image is connected, what we showed is that a connected subset of R, an equivalent way of talking about a connected subset of the reals, is that if you have any 2 points in that subset, then everything in between those 2 points has to also be in that subset. Okay, so since the image of this interval is connected, right, so this set here is connected, and these 2 points are in that set, that means everything in the middle is going to have to be there. And so everything in here has to indeed, as it appears in the picture, be in this set. So if we have some y that's in here, so if we have some y between f of a and f of b, then that y has to be in f of s. So there has to be some x which is mapping to this y. Okay, so it just is basically comes down to the fact that this interval being connected has a connected image, and then we have a characterization of connected subsets of the reals. So to turn to the proof, so we're first going to recall that a subset of R is connected. This is one of the theorems that we proved about connectedness. A subset of R is connected if and only if it has the property that if alpha, so if alpha is less than gamma is less than beta, and alpha and beta are in the set, then so is gamma. Okay, so if you have any two things in the set, everything in between those two things has to be in the set as well if the set is connected. And in fact, that's an equivalent way of saying that the set is connected in R. Okay, so, well, so in particular, so maybe I'll expand on this. In particular, any interval has this property, right? An interval has the property that if you take any two things in it, everything in between those two things is in it as well. So any interval is connected. So in particular, R and any kind of interval in R are all connected. Okay, so now let's begin the proof proper. So since f is continuous and our interval is connected, the previous theorem implies that f of AB is connected. Well, then since f of A and f of B are in f of AB, and f of A is less than y is less than f of B, it immediately follows that y is in this connected set f of AB, i.e. y equals f of x for some, well, it's really x in the closed interval AB, but of course we explicitly said y is not f of A or f of B. So it's some x in the open interval from A to B. And that's it. Okay, so again, this is another proof, which is incredibly straightforward once you've done a lot of hard work and clarified many foundational issues about the reals. So the fact that intervals of the reals are connected really comes down to the completeness axiom again. And we have our careful definition of f being continuous, the quite careful discussion of connected sets. So this is all, this simple proof rests on a quite a wide, broad foundation of difficult foundational work. Okay, so this, again, kind of a marvel to be wondered at how simple this is after everything we've gone through. So one nice application of the intermediate value theorem is the existence of roots. So we discussed this a bit in the beginning of the course when we were talking about completeness, and we showed that square roots exist. and indicated that nth roots exist. But now we can actually give a rather quick proof of this. So let's take a b in a non-negative real number and a natural number n. Then there is a unique y, also a non-negative real number, such that the nth power of y is equal to b. In other words, the nth root of b is this y, right? So we write y is b to the 1 over n, and or the nth root of b, like this, familiar notation. So let's take a look at the proof. So basically what we want to say is that if we consider the function, or we're trying to say that we're trying to find this y, right? Given this b, we want to produce this y, but that's what the intermediate value theorem is good at doing, right? So given something, it's good at producing something which is, it's good at producing some x such that y is equal to f of that x. So the thing you started with is in the image of this function. So what we have here is we want to produce something such that this b is in the image of the nth power function, right? So what we're going to do is just consider that nth power function. So define f of x equals x to the n, which we know to be a continuous function. A continuous function on all the real numbers. And let's just assume that b is greater than 0, since the b equals 0 case is trivial. Okay, so what we want to do basically is take this b and we want to trap it between two values of the f function, right? This nth power function. So what we can do is take f of 0, right? F of 0 equals 0. That's less than b if we consider b greater than 0. And then we just have to find f of something which is bigger than this b, right? So we just have to find this mystery thing. Okay, so note that f of 0 equals 0, and that's less than b. So I guess I can say note first that f of 0 equals 0, which is less than b. So now we can just consider cases. So if b is less than 1, then b is less than, well, 1 is f of 1, right? So then b is less than f of 1. If b is bigger than or equal to 1, then b is less than f of 2b, since f of 2b equals 2 to the n, b to the n, and b to the n, when b is bigger than or equal to 1, b to the n is bigger than or equal to b, right? So this is bigger than or equal to 2 to the n times b, and that's bigger than or equal to, right, 2 times b, which is bigger than b. Okay, so in any case, there is an interval zero, comma, I don't know what letter I want to use, 0, comma, c, such that f of 0 is less than b is less than f of c. So by the intermediate value theorem, b equals f of y for some y, i.e. b equals y to the n. And then we just would like to see that this y is actually unique. And one reason to say that is to say that this operation, this notation b to the 1 over n, that defines a function, right? There's a unique non-negative real number associated to this b and this natural number n. So we can define a function there to see that y is unique. Suppose that y1 to the n equals y2 to the n equals b. Well, then 0 is equal to y1 to the n minus y2 to the n. And there's a factorization of this. This is y1 minus y2 times y1 to the n minus 1 plus y1 to the n minus 2 times y2 plus, and then the powers of the y1 decrease while the powers of the y2 increase. So this goes up to, you have y1, y2 to the n minus 2, and then plus y2 to the n minus 1. And so what we have here is the product of two things being equal to 0. And what we can notice is this second term is non-negative here because it's just a sum of non-negative terms, right? Each of these products is just a product of two non-negative numbers. Remember, our y is a non-negative real number, right? So each of these y's is non-negative. And so that means that the only way this thing is 0 is if y1 and y2 are both 0, right? So every single term has to be 0. In particular, y1 to this power and y2 to this power is 0, and so y1 and y2 are 0. Okay, so notice the second term, the second multiplicand is 0 if and only if y1 equals y2 equals 0, right? So in this case, we have uniqueness. Have uniqueness in this case. If it's not 0, if the second multiplicand is not 0, we can divide by it. And immediately obtain y1 equals y2. So y is unique. Okay. And so this allows us to define, so this corollary allows us to define a function from the non-negative reals to the non-negative reals by f of x equals x to the 1 over n. Okay, so we needed to know that there was a unique output there, right? A unique y associated to your b. The last thing I want to talk about is an alternate proof of the intermediate value theorem. So this alternate proof is quite a bit simpler. It doesn't rely on the preservation of connectedness by continuous functions. So you might guess, I mean, that preservation of connectedness by continuous functions is a quite general result. The intermediate value theorem is quite down-to-earth type of thing, very simple to understand. You don't need any fancy definitions like connectedness. So you might wonder, what's sort of the simplest possible proof you could come up with of this quite fundamental theorem. And so the book gives one using, actually gives two. So it gives us one proof of the axiom using the axiom of completeness, and here's my version of it. So we want to use the axiom of completeness to prove the intermediate value theorem. So in other words, we want to use the least upper bound property, right? So we have to somehow, we're going to produce this x, which is whose image under this function f is y. Naturally enough, this x should be the least upper bound. It should be the supremum of some kind of set. Right, so it should be the supremum of some set lying in this interval from a to b. So to get a sense for the idea of this proof, I've drawn a little picture here. So we have our continuous function f, the graph of it drawn, and we have f of a less than f of b, right, and we have some value y in between f of a and f of b. Now kind of indicated, if we go across the graph at y, horizontally, then we locate three values of x which attain this value of y. Right? And we have to show, logically that these values of x actually exist, that at least one of these values of x actually exists. And we want to do this using the axiom of completeness. Right? So we want to write at least one of these x as the supremum of some natural set. So in this picture, x3 seems like the most natural one to try to write as the supremum of some set. And what it's the supremum of, it's the supremum of the set of values, the set of stuff in this interval AB that is less than y, right? So if we look at the part of the graph here, which is under this value y, so we have this part here and we have this part here. So if I graph those segments in the interval AB, right, we get this green stuff here. And we see naturally from the picture that x3 is the supremum of that set of green stuff. So that suggests doing the following, or something like it. So we'll define the set A to be, and maybe I'll write A in green here just to reflect the picture. So A is going to be the set of x in the interval AB, x in AB such that f of x is less than y. Okay, so this is called a sub-level set of the function f. Okay, so first of all, let's see that this set is non-empty and bounded above. So A is non-empty. A is non-empty since little a is in A. Right? You can kind of see that in the picture, and it's obvious because f of A is less than y from our setup here. Okay, and it's also bounded above. Also bounded above, well, that's obvious because we've defined it to be a subset of this closed and bounded interval. It's also bounded above by B. Thus, by the axiom of completeness, it has a supremum, a least upper bound. S equals sup of A. So what we'd like to do, we'd like to show that f of s must in fact be equal to y. And how we'll do this is we'll rule out the idea that f of s is greater than y and less than y. We do this by ruling out f of s less than y and f of s greater than y by contradiction. All right, so here's the basic idea for this. So let's say here's S. And let's look at the first case, f of s is less than y. Okay, so we have our function f mapping here. So we have f of x, and we have y. If f of s is less than y, here's where the continuity of f comes in. If f of s is less than y, we can put a little epsilon ball here. So we can put an epsilon ball, as this is f of s plus epsilon, f of s minus epsilon. And then we can find a little delta ball around s. And so we can find it, we have s plus delta, s minus delta, which maps into that epsilon ball. All right, so this delta ball is being mapped into here. Okay, so that should mean that a little bit to the left and to the right of s, the values of f are still less than y. Right, so in other words, f is less than y, so conclude that f is less than y through a neighborhood of s. But what's the problem with that? Well, s is supposed to be, well, that would mean that in this neighborhood of s, that those are all points of a, right? If the value of the function is less than y on some points, those points are in a. Right, so this would imply that the neighborhood is contained in the set A. But that violates the fact that S is supposed to be a least upper bound of A, right? It violates the fact that S is an upper bound of A. But this contradicts the fact that S is an upper bound. Or I guess to use my shorthand, so this is a contradiction to the fact that A is bounded above by S. So you see that? Okay, so there's going to be points over here which are landing in here. So that's going to be less than y. So that means there's points over here in the set A, but S is supposed to be the furthest thing in the right, to the right in the set A. And then, so this is the case where f of s is less than y. And there's a similar idea for f of s greater than y. And so if f of s is greater than y, then there's going to be a little neighborhood. So this is going to imply that f is bigger than y through a neighborhood of s. But the problem with that is any neighborhood of S is supposed to contain points of A. Contains points of A. Since it's the least upper bound. And so this is a contradiction. Because if there's points of A in this neighborhood, then f of those points is supposed to be less than y, but we just said that f is greater than y throughout this neighborhood. So that is the kind of outline of the idea And this little argument kind of relies on the fact that S is in the interior of this interval A to B. We want to be able to go to the left and the right of S. So one thing we'll need to rule out is that S is not A and S is not B. And so to do all this, basically we have kind of a lemma here, which is that if the value of a continuous function satisfies some strict inequality, then that strict inequality continues being true throughout a neighborhood of S. So there's a useful little lemma hiding in here. So here's the lemma formally stated. If you have a function from some set A in Rn to R, and your function is continuous at this point C in A, what we're going to do is suppose that f of c is less than y, then you can maintain this inequality throughout a neighborhood of C, essentially. So in other words, there's some delta such that the ball of radius c around delta, we look at all the points in A within that distance delta of c, then the function value on any one of those points is less than y. So the image of this set is bounded above by y strictly. And the proof of the lemma is straightforward. So the proof of the lemma is straightforward. So we just let epsilon be equal to y minus f of c. Then there is a delta greater than 0 such that let's say x in A and distance between x and c less than delta implies that f of x minus f of c is less than epsilon. So in particular, we have f of x minus f of c is less than, right, so we have both of these, so f of x minus f of c plus or minus that quantity, both of them are less than epsilon. So in particular, this one is less than epsilon, and epsilon is equal to y minus f of c, i.e. f of x is less than y. And so taking into account where x is in the set A, and it's also in the delta ball around C, the f value of that is less than y. That implies the conclusion. Okay, so we have this nice lemma. We can maintain inequalities throughout a neighborhood when we have continuity at a point. Okay, so back to the proof. We're trying to rule out the value of the function on this supremum being less than y and greater than y. So returning to the proof of the theorem, to the proof of the theorem, or of IVT, we first note that S cannot be A or B. So the reason it can't be A is since f of A is less than y, f of x must be less than y for x in A comma A plus delta, right? We must be able to extend this inequality a little bit throughout this interval. So that means, i.e. A comma A plus delta is contained in the set A. So thus S is bigger than or equal to A plus delta, and that's bigger than A. So S can't be A because S is strictly bigger than A. On the other hand, f of B is bigger than Y, so f of x is bigger than y for x in b minus delta comma b. Right, again, we can extend this inequality throughout a small neighborhood of b. So what this means, this means that this interval, b minus delta b, that has no points of a in it, right? By definition, a is everything that is that maps to be less than y, and everything in this set maps to be greater than y. And in particular, every element of this interval must be an upper bound of A, is an upper bound. Right? A is this subset of the interval from A to B, but it must, this subset A then, since it doesn't intersect this at all, must lie completely to the left of this little interval. And in particular, B can't be the least upper bound, right? Since everything in here is an upper bound, so, B is an upper bound, but it's not the least upper bound because there are lesser elements than B in this interval, which are also upper bounds. So this implies that B is not equal to S. Okay, so thus S is in the open interval from A to B. Now suppose that f of S is less than y. Well, then f of S minus delta, S plus delta, is less than y for some delta. So in other words, so this implies, this means that any number, so anything in the interval from S to S plus delta is contained in A. In particular, S is not a least upper, or is not an upper bound for A. In particular, S is not an upper bound for A. And that's a contradiction. So suppose that f of S is greater than y. Then f of S minus delta, S plus delta, is greater than y for some delta greater than 0. Well, since S is the sup of A, there must be elements of A or at least some element, it must be an element A in A, which is in the interval S minus delta comma S. But then f of A is less than y by definition, while f of A is greater than y by assumption, or well, by what we deduced above, by the above, again a contradiction. And thus f of S equals y. And that completes the proof of the intermediate value theorem again. Okay, so the book also gives another proof of the intermediate value theorem, actually just outlines a proof. That proof is much simpler. It's based on the nested interval property. And in fact, the book says that the proof only depends on the nested interval property. It really depends on the Archimedean property as well. So it's not just the nested interval property, the proof that they outline. But in any case, that I might assign that as an exercise for homework to fill in the details of that proof. But this proof is a little bit more involved, and the book just leaves the details again to the exercises, which I don't know whether that's a pedagogically sound move or not. So I wanted to go over that proof carefully here. All right, that's going to be it for this lecture.